First, maybe start with the quick questions. Who have already used DynamoDB developing your apps? Quite a few. Any beginners on DynamoDB or NoSQL? A few. So I will start with the core concept and then go into more deep dive, developer-oriented, and probably we'll finish on a few new features from re:Invent, a touch point this morning on the other session if you were already in. It's probably going to be a repeat for this. My name is Bastien Leblanc. I'm a solution architect at AWS for the last 2 years. And before that, I've got a quite strong database background. So probably that's why I'm very passionate about this, but more around the relation database like Oracle and SQL. OK, so let's get started. So today it's really how to dive in and how to dig into your actual application and to use DynamoDB at its best. Because it's quite peculiar, it's quite different from what you've seen, even if you've been doing some NoSQL on MongoDB or Cassandra. There's a few very specific to DynamoDB that we are going to go through. So the session is called Schema Design. But wait, DynamoDB was supposed to be schemaless. And as a developer, you were probably used to the, well, it's just a stuff where I put my data in. And actually, you should care. You should care because of performance and because of cost. You are in the cloud, so everything that you do has cost. And cost has also other consequences. So everything is schemaless, but you still need to do the schema design. So the old way was about relational database was to do, normalize until it hurts, and just denormalize really when it's needed. Just because, well, it used to be built back in the days where the disks were quite cheap, so that was okay to have all the data on separated in multiple tables. But now, NoSQL, aggregate, denormalize until it works. There's one important thing in DynamoDB that you were probably not used to is when you start to design, you have to start from the business answer that you want to answer, and not from your data. That's very important, and I will just repeat this the whole session, because that's really different, and you should never start by designing your table if you don't know what answer you want to, what questions you want to answer. And what I mean by that is you have to design your table based on your access patterns, because before that you were used to, well, you create the schema based on your data, on your business. Yeah, well, an order contains all the lines, so I would create 2 tables or lines. Makes sense. But then always go back to the actual question you want to answer and not the other way around. So a bit of history. That's my background also. SQL, probably a lot started with SQL database. So like I said, the disk was cheap at this time. So the idea was to eliminate redundancy and try to have the lowest footprint. Second thing is to ensure data integrity on your database. And that's another important point, is that with SQL, you were putting a lot of business rules in your database, foreign keys, triggers, even codes, stored procedures, things that actually matter for your business was embedded in the database. And you end up having, and we have a lot of customers having this big monolith, big database on Oracle or SQL or others that are impossible to manage because everything is tied into the schema, and every time you change the business rules, then you have to go back to your schema design. You used to build relationships, foreign keys, and normalize as much as possible with this very probably known by some of you, first normal form. In NoSQL, we are like changing gears completely and talking about completely different things. First, we don't bother about size in terms of disk, because now the disks are cheap, and you can, sorry, the compute are cheap, so you can have more compute to process your data. Some key features, so data size. Size matter because of partitions. We'll go back to this concept of partition and DynamoDB, but one partition is 10 gig of data. So consider to size your database properly. Shape, I would say the only thing is shape for queries. Again, you answer your questions, so look at how you will query your data first. Data velocity. DynamoDB was designed to be low latency, and it's probably where it excels is doing transactional fast, very, very fast queries. When we say fast, it's milliseconds or until microseconds using some cache layer in front of DynamoDB. It's not meant for large queries that takes seconds or minutes or hours. That's probably, if your query takes this time, it's either you have badly designed your DynamoDB or it's not the right database to use. We have this concept at AWS as purpose-built databases, that every database has to serve one purpose, and you shouldn't do everything with Dynamo. Dynamo is perfect for transactional, low latency queries, but not for analytics. It's good for time series, even though now we have a time series database that is even better than using DynamoDB. And it's not meant for very strong integrity rules that you have to put in a relationship database. Keep your data together. Because everything is, you want to reduce as much as possible the number of queries you do on Dynamo. If you put all your data together in one item, then you reduce your numbers of queries. Because if you do several tables, if you spread your data that you used to do in SQL, like having orders, all the lines in 2 tables, that's 2 queries on Dynamo. And then 2 latencies, and then cost, etc. Use sort, use GSI. I will explain later what is GSI, global storage, global index, sort keys, and distributed queries. So again, start from your access patterns and not from your data. That's really important. Okay. So a few minutes on core concept, just to make everyone at the same page on DynamoDB. So it's a fully managed NoSQL database that provides fast and predictable performances. Predictable that you have always the same latency. And seamless scalability. All this is right if you design it properly. If you don't design it properly, you won't get the latency that Dynamo can excel in. So we don't have a concept of database. When in Dynamo you create a table, and in this table you create items, and these items have attributes. One of the core principles is usually what we say is one good application, one good design is to have only one table for your whole application. Instead of, that's very different from what we see in relations. This table have a primary key. Primary key can be just simple. Primary key only. In this case, it has to be unique because that's how you would identify your item. Or can be a composite of a partition key and a sort key. It's called it's called partition key for a reason. It's because behind the scene, that's how we partition your data across multiple shards, nodes. So make sure that you design your partition key to be the most effective. And the most effective primary key is to be evenly on your data, that you will have all your queries spread across all nodes. You want to avoid having what we call hotkey on one partition. So one example of bad partition key would be the date. If you insert data having a partition key as a date, because you could think as you create invoices, well, the first key would be date and some number of invoice. But if you do that, then all your invoices of the day will end up in one partition. So you will always end up working on one partition only. To instead use something that is really spread, for example, customer ID, because you will probably use a lot of customers' ID. Okay. Second important core component is the indexes. Thing to understand is indexes in DynamoDB are very different from relational database indexes. It's not meant to access the data, it's meant to store data in different ways. So think about indexes as a copy of your data, especially global secondary indexes as your copy of the data for a different access pattern. And we will see that in examples. So it's not, so in relational database, when you access an index, it's just to give you the pointer to the actual data. When you access data on the GSI, on DynamoDB, you access exactly the data that you want. So yeah, again, indexes, I like to see that as a view, a materialized view of your data. Last two things, RCU and WCU, read and write unit. It's how we price DynamoDB. It has changed since 2 weeks ago at reInvent because we announced that we can use on demand. So pricing, I will explain a bit more later, but basically we price per read and per write unit on your database, on your table. And each table and each global index can have a different write and read throughput. That's very important to design to be able to minimize cost and still get your throughput right on your DynamoDB table. Okay, let's go into some example. First, a quite simple example. You are storing people. You have a security social number as a primary key attribute. It works well because you have very good selectivity on your social security number. That's unique. You're sure it's unique, and it's spread across the whole population of people. Okay, that's easy. You don't have. Now that if we want to add a relation to, let's go to this one first. So you still have these people, but then you start to think about having one person definition and one job definition. In a relational schema, you would think about creating two tables. One would be persons, one would be jobs, joining by your social security number. What you actually do is use the partition key, still unique, and use the sort key as we call non-homogeneous to store different things, person and professions, or skills, and then you are still going, like I said, one table. You embrace the ambiguity because here you have a column that represents two different things, persons or professions, and here you have completely different data. But you still have everything in one place. So if you want to search for this specific person, you get everything in one query. If you query only on the partition key, you get everything in one query. If you query on the just a professional, you can get only the occupation. One more probably simpler example, that's a one-to-one relationship again, because it's devices and measurements. So you will get the devices as a partition key, but that's not unique. It's quite spread because you probably have 10,000 of sensors, but it's not unique. So you have to add another column to have the uniqueness between partition key and sort key, and the sort key could be the timestamp, the epoch. Because you probably will query again against the last measurements per device, because you want to display, when you display the temperature in the room, you don't want to query that 2 years ago. You will query the day or the last 24 hours. So that works very well in Dynamo when you query a partition key and a sort key with a greater than or less than. Because as it's written, it's a sort key. So the data is sorted against this key in the partition. So you will get all your device, one device will be in one partition and sorted by timestamp. So that will be very efficient to query if you query only the last n minutes. Okay, so if we go a bit further to this example, this probably sounds a bit weird if you've been used to designing complex schema. So that's a HR schema. Probably sounds weird to store in the same table the job titles, where the employee works, what is his compensation, what name, security social number, etc. So you have very different information stored in one table. So the problem would be, so that's all the first answer that we said, use only one table. But if you want to query, let's say, I want to search on the employee name. I'm the HR guy, I'm looking for employee name. If you don't do anything, if you're looking for the employee name, well, you don't have the employee ID, so you will search, you will actually scan the whole table, so the whole nodes, to get only the employee name, Murphy. So that doesn't work. Doesn't work in terms of efficiency. So what we will do is create a GSI, a global secondary index, on top of this table to solve the access pattern that we want to query. So we will actually create a global secondary index on the sort key as the partition key of the global secondary index, and having the sort key here. So you end up having a global index on this partition key and this as a sort key. So if I want to search for an employee name called Murphy, I can do a query on only the employee name global secondary index partition and scan for the employee name Murphy. And this, I reduced a lot the numbers of throughput I need because I only queried on employee name. And that can be also very efficient if you have like very empty attributes for this, like this. So now we have talked about one-to-n relationships, so how to get n-to-m relationships. And that's start to be a bit more complex because we still want to use only one table as a DynamoDB principle. And this is a very typical example of invoices and bills. One invoice can contain multiple bills, and one bill can be paid by multiple invoices. So you have an n-to-m relationship. So actually what we do is create the table with partition key and the sort keys having exactly the same attribute type, which could be invoice or bills. And then you create the GSI on the other partition. So if you create, the GSI will be on this column, and the data will be on the partition keys. So you create a GSI on the opposite of your table. And this way you can query in one access, so coming from one invoice or coming from one bill. And in the table, you will get the attributes of each of the actual items. And in GSI, you can choose which projected attributes you put in. That's very powerful, quite easy to implement, and that solves the problem of having, I want to display one invoice and all the bills attached to it, and also I've got a bill and I need to reconcile this to which invoices actually match this bill. So I talked about projections attributes. So that's a very, probably seems complex like this, but it's quite straightforward probably, is when you create an index, you choose which attributes you project in it. So you don't need to create an index with all the keys, but you can. And of course, if you create an index with all the attributes in it, then you get more storage cost. But then there's the other parameter, is how many RCU you will use. And the idea here is you have to think about your access pattern and which data you actually want when you query your index, or you query your database, your table, is you have to put everything that you need in the global storage index, the GSI, but nothing more. Because if you put everything, then you have a storage cost that goes up. And instead, if you put only the attributes that you need, then you get a good balance. And the other side of the chart is to talk about fetching cost and writing cost. That probably makes sense for a lot of you who use databases before. If you have more data to write, when the cost is higher. But you get less fetching cost because you have everything in your index, in your GSI, so you don't need to query again the table and do a longer, a more expensive fetch. Again, maximize performance and minimize throughput cost. That's all you want to do. Sparse index, because you want to reduce your read capacity unit and having less throughput, let's take this probably quite typical example of gaming, and it can be applicable to something else probably. So you have a table containing all the players and every game it has played with scores, date, and an award. Okay? That's all well, but that's probably going to be a large table if you have a very successful game. And let's say now I want to display every gamers that won an award. If I don't do anything, I will have to scan the whole very large table to fetch only this field. And what we actually do is, if you create a GSI as a primary key, the award, we create what we call a sparse index, because the GSI will be very small, because it will store only the lines that have actually a data in it. So make sure that you don't store something here like no, 0, whatever. Don't store at all the attribute if there's no data. And then you get a sparse index, a sparse GSI. And this GSI will be probably very small and will be updated automatically. Yeah, one thing to note on the, so I talked a lot about GSI. There's also the LSI, the local storage index, that are local to a partition. So GSI is global, and LSI is local to a specific partition. So it shares the same partition key, and you only index another sort key. And again, you can use the same principle of if I index a field that is not often filled, you get a very effective index because it will be very small and then better latency and less cost. So that's a more advanced example of a writing problem. If you want to write heavily on a table, then you can get quite limited on the throughput, or you will pay a lot on write capacity you need just to get things written. So the idea is to create a GSI on a random key here from 0 to n. N has to be defined based on your application and how many threads you can have to write. And if you have, like, say, 100 threads or 100 nodes or application server or something that writes to the database, then you assign this particular hash from 0 to n, and then you spread the write evenly on the whole partition. The idea here is, so when you write to a table, we update the GSI for you. And we update the GSI in an asynchronous manner. So a GSI has an eventual consistent read. Because when you write to the table, we don't write to the GSI as we write in asynchronous mode. So if you have a very heavy write in one table, you can end up having quite significant delay here if you don't do this kind of trick. Yeah, it's kind of a trick to spread more loads on more partitions. And probably the question you have is, how do I query this? Because now I have this partition key that doesn't make sense. It's just a random number between 0 and 100. So during this, you have some more heavy lifting to do when you read. And what you actually do is having n readers go back to the same principles, having 0 to n readers in parallel, and doing everyone will scan the data. So that's very handy if you do writes heavy, but that's not very efficient for read workloads. The last example I have for you is time series. And we still talk about this, even though you probably heard this morning about TimeStream, the new time series database at Amazon. I still think that DynamoDB can handle quite good the time series if you do it properly. So classical example of time series is for every x seconds or milliseconds you store attributes. So it makes sense to store this as a partition key, the date, and sort key, the timestamp, and all the attributes later on. And the trick for time series is to store only the current date in one table with a very high write unit and quite high read unit, because your application will probably read a lot and write a lot at the current day, But then when you move to archive, well, you don't need that much data. So what you end up doing is having a second table. That's probably the only position where you can have several tables for the same purpose. It's a bit specific. So here you create another table for the previous days, depending on your requirements. Maybe you need 24 hours, maybe you need 7 days. And here you can reduce the write to 1, because that's just an archive. So you are sure you will never write again in this table. And you still have a quite read heavy, because your application will probably display the last 30 days. So, and then you have probably another table, and the numbers of tables here depends on your use case. And the older table will be probably after 30 days and provision only to 1 read and 1 write capacity. There's one problem here, is how do you update data from one to another? Because you have, if we go back here, you have a component that writes heavily on the table all the time. So how do you get the updates? Well, how do you remove the data here and create it here? And probably the best way to do that is to use TTLs. So when you create a table, you can assign a TTL, a time to live, for every item to say, well, in this table, I will expire after 1 day. So we will take care of deleting this item after 1 day. Okay, so we solved the delete problem, but how do you get the data here? Is to use another component of DynamoDB, which is called DynamoDB Streams. DynamoDB Streams is a component that takes every changes in your table and write it on a stream, similar to a Kinesis stream. And with the TTL, you get a specific event, which is called a TTL delete, which tells you, oh, I deleted the data here. This is the data I've just deleted. And from your stream, you subscribe, for example, a Lambda function that reads from this stream and will take all the TTL on delete data and writes to the second table. You probably can stick to write 1. You may get throttled, you may get some latency here. It's probably fine, it's just archive. You just want this to be done. And you can have a second stream on this one, a second TTL and a second stream that writes to the archive table. So that's probably a lot on the design schema, but I will have at least probably 10-15 minutes for questions at the end. I want you to touch point a bit on the new releases of re:Invent a few weeks ago. And the first one is transactions. Transactions used back before this, there was a lot of libraries that done that before. So a transaction is to be able to do multiple updates in a consistent ACID manner. So you want to update several fields, and if the last update fails, you want to roll back the whole transactions. It's very good in finance, but even in games or in a lot of contexts, you need this consistency in transactions. So that works in any items, in any table. That's available now. So we have just new 2 APIs called transact write items and transact get items. They are ACID, means atomic, consistent, isolation, and durability. So it's atomic, that means that all the updates are done once or not. You don't get inconsistency if one update fails. And durability, well, DynamoDB is spread across availability zones, and we ensure this durability that when you have the transaction that is committed, you are sure that the data is in. And without the ugly things, if you are familiar with some things in relational database like deadlocks, running transactions, unfinished transactions, we don't have this simply because we implemented transactions in a very simple manner. So, and a very simple manner because there's one thing to know is, no, that's later, it's that we don't lock the item when you do the transaction, right? So that's why you can't get deadlocks, because we don't lock the item. You don't get a problem of long-running transactions because we are in a low latency table, and even if it would happen, it's not an issue because it's not locked. And DBA pane, well, we are in a full managed service, so you don't have anything to consider or to work around or to monitor from your DBA perspective. So how does it work? Very simple example of a gamer. You get status from this specific gamer with two fields, health and that's worked well. That's just the query, and you return everything for either for two status or for the whole gamer. That worked well. But now, if I need to update two attributes from the same player, if before the transaction I could do two updates, that's fine. But I don't want in this example, I don't want the coins to be debited if the health is not updated. For example, I don't know, you had a portion that decrease your cost, your points, your coins points, and you don't want the health to be related. So very simple. That's the transaction API. You just put the two updates, and you are sure that the two updates are done either together or not done at all. So like I said, the most important things to remember is that items are not locked during the transactions. Which means that if you have, in your example here, something else, another event that tries to modify one of these attributes during the transactions, your transaction will be in failed mode because we can't have a consistent answer. Then that means that your transaction is failed. So you have to deal that in your application. And that's very different from a relational database transaction. So you have an extension to deal with, and that's your application to work around or to work about what to do when the transaction fails. The last topic and the last feature that was released at re:Invent is called DynamoDB on demand. So I talked a lot about read and write capacity before, the whole talk. And so we used to buy reserved capacity, read capacity and write capacity for your table. Okay? And you could auto-scale. You could say, my table is only used during the day, so I will provision more read or more write to a specific table and scale down to in the night. Now you have two choices. Either you stick to the provisioned mode, so you will decide, like we've done for the time series, you will decide my table for the day is very write heavy, so I need probably 700 write, and the other I don't need a lot. Or you don't know what's going to be your requirements on read and write. And you have this very nice and easy button called On Demand. That's the price. That means that we will do everything for adapting the capacity based on your request. So you only pay for what you use. So that's very good. So when you create on demand, it's when you create new tables and you don't know your workload, you don't know how many people you will use, you have very unpredictable application traffic. Maybe you have a website, but it can be very used or not, depends on a promotion or a social media thing, but it's not meant for when you have predictable traffic. I would still advise you to stick to a predictable provision manner if you know actually how you will use your application. So that's why we keep the two model. It's easier to predict cost. It's easier to make sure that you will not have any throttle on your application if you know exactly how many read or write you will do on your application. So I think we will have a lot of production environment stick to provisioned because you need some predictable thing. But when you start, you can start on demand, and you can always switch from one to another, one time or the other. So start with on demand, start your development on demand, look at how many capacity you have, and switch to provisioned when you have a more predictable workload. So to wrap up, let's go back to this first slide that I mentioned. And that's the principle of make sure that you use the right size of your item, that you put all your data together in one table as much as possible. Look at your access pattern, what is your velocity required. If you really require a very, very low latency, you can have a cache layer in front of Dynamo called DAX. Then you can achieve microseconds latency and still doing it right through this cache. Use the sort orders. So design your table with primary key in mind to spread the load on primary key, but think about the sort key. As the name implies, it's how the data is sorted, so make sure that you will query this field and use the fact that it's sorted on this, like a timestamp, like an age, like a game ID, or something that is a query that you will query on directly. Use GSI for all the access pattern. So having one table for the primary usage, and when you have a new requirements, when you can think about creating a GSI to answer these new questions, which is probably very different from the main table. To wrap up, so that's the DynamoDB streams here on the top. And like I said, the idea is that think about DynamoDB for solving one problem or solving a few problems, but DynamoDB will not solve every problem for you. You may have some analytics to do on your data. And if we take, again, the time series example with the whole archive from a few years, from thousands of sensors, and you want to do aggregates, or you want to make some anomaly detections or things that are really scan heavy, in that case, you shouldn't do queries on Dynamo because it would be a scan, and a scan is very expensive. It's not predictable. It's not meant for this. So what you probably should do is having a separate database or search engine or something else that works really well for solving your analytics problem, or if you want to do machine learnings on your data, or if you want to do search on your data. And with these very powerful streams, every changes can be pushed to something else. So if you have new data coming in, that's worked very well for the transactions, for your day-to-day things on your application. And then you want to create a search engine, use Cloud Search or Elasticsearch probably to create the search engine. That we have a lot of customers in retail do that. So it's having Dynamo for the order management, the customer-facing order management system, because they query only on orders or customers or product ID. That works very well. But then, if you want to create a search engine for your customers to search for description or attributes or things that are down in the attributes, that doesn't work for DynamoDB. So create a search engine that uses something else, like Elasticsearch. I wanted to finish on this. We have it's a developer conference, so I suppose that you all know Slack, and we created a AWS developers Slack. Probably you have heard this morning already, and we have a hashtag databases channel, but for now it's only on invite. So if you want to have an invite, you have to DM this guy called Rick. You probably saw him earlier in the day, or come message me also. I can do that. And we have about 10 minutes for Q&A. I'm happy to take Q&A or time. Yes.
Sorry. When you choose on-demand option, can you still set maximum capacity just to prevent from going over budget, for example?
Okay. Yeah. So the question is, for on-demand, can we add a maximum capacity? The answer is no. I don't think it's possible, but we can check afterwards. It's a bit like a lot of on-demand services on AWS. You have to make sure that you have other guardrails, like billing and things around it. But the idea is that it will scale, because you want to have the table to scale for unpredictable. So if you have these specific requirements, go back to provisions. Yes?
Hi. The global indexing,
yes.
Does it have to be decided from the outset, or can it be applied later on as you use your...
Yes. So the question is, the GSI, the global indexes, can be added afterwards. The answer is yes. When you create a table, it actually doesn't have any indexes, and you create the GSIs later on. There's one big limitation, is that you only have 5 GSIs possible on one table. So you can create them later. And that's why I talked a lot also about GSI overloading. Make sure that you can use one GSI with several completely different information in it. Like when we have the employee name and the job title in the same GSI, then you can go around the 5 limits. Yes.
What happens when you have provisioned a certain amount and you get a bit more traffic than that? What happens to the rest of the traffic?
So the question is, what happens if you go over your reserved capacity? So let's say you have 500 read capacity. If you go over, it gets throttled. So when a query is throttled, the API answers right back that it can't serve you, and that's the application to retry. So if you use the AWS SDK, it's integrated in it. So what you get is latency, basically, or even errors after a certain amount of time. But you get latency because your request is throttled. So say, nope, I'm over capacity. Go back later. You try again later on. So you get capacity. There's one thing in Dynamo is that we have burstable capacity, so you can go a bit above your read capacity. It's exactly the same as T2 and T3, is that you can go a bit above your capacity for a certain period of time because you have this reserve capacity, but it doesn't work for a long time. Answers your question?
That's up to the developer to implement that, go back and try again.
No, that if you use the SDK, it's integrated in it. The retry, the exponential time before each retry is integrated in the SDK. That's why I'm saying from the developer perspective, you get a latency. Your request will get more. Yeah. Okay. Well, I'm around afterwards for other questions if you need to. Thank you, everyone.